Hello everyone, how are you? I hope you're doing really well. In today's class, we're gonna see some examples on the squeeze theorem. In the last class, we studied what was that, why was that important, we have to use that, okay? Now, the first point which I already mentioned in the last class was that whenever you see product of two functions, the first thing that you tend to do is to use the product rule of limits. Okay, that is limit of this multiplied by limit of this and then get to the answer. But that thing works in like some limits and it doesn't work in other limits. Like in this case, the product rule of limits will not work. Okay, use that. So limit x approaches to 0 of this function, use the product rule. We have two functions, this one and this one. Okay, so it is limit x approaches to 0 of this function, okay, times limit x approaches to 0 of this function. Okay, now put 0 here, simply it will give me 0. Put 0 here, it will give me what? Sine pi by 0. Now pi by 0 is an undefined number. Sine of undefined is again undefined, and we are multiplying 0 with an undefined number. It will be what? 0? 0 multiplied by anything is 0. No, this is undefined again. So remember this thing, 0 multiplied by with a defined number, any real number, any complex number, it will be what? It will be 0. But 0 multiplied by any undefined number, we cannot define what that number is. It is again undefined. Okay, so that is why we can say that. Okay, so like this we are not able to evaluate the limit. So here comes the squeeze theorem. Okay, so in those cases where the product rule doesn't work, we'll go for the squeeze theorem. We'll think about the squeeze theorem, that whether this question is about the squeeze theorem or not. Okay, so in order to solve this problem based on the squeeze theorem, now you know what squeeze theorem is, you all know. Okay, so I'm gonna just give a quick review of that. If we have two functions, let us say f of x and g of x, and we have a third function, let us say capital F of x, and this function lies between these two functions, like over an interval, let us say from the values of x a to b. Okay, this inequality holds true. Then what's gonna happen, that I'm gonna take any number between these two intervals. Let us say it's c belongs to this interval, okay, a comma b, and if I'm going to evaluate the limit x approaches to c of this function f of x, it's gonna give me, let us say, p. And if I'm going to evaluate on the same number, okay, its limit, and it's gonna give me p. Then if this inequality is correct and this thing is correct, like the limit of x approaches to the same number of these two functions, like the limits are equal, then squeeze theorem gives us this limit on the same number but of this function as p. Okay, this is basically the overview of the squeeze theorem, like how to use it. Okay, now using graphical illustrations, we've already done that in the previous class, so I'm going to solve this now. So think about like how to just solve it using squeeze theorem. Okay, so first of all, what do I need in squeeze theorem? What do I need? I need an inequality. Okay, I need an inequality. I need a function which lies between two other functions. Okay, so here in this, like looking at this full function, how can you form an inequality? How? Use this sine function. Okay, 0 pi by 2, pi, 3 pi by 2, and this is 2 pi, 90, 180, 270 and 360 degrees. Okay, this is in radians, you know this, you've studied in your grade 10. And this is 1 and this is -1. How sine function behaves? Like this, you know it. Okay, so like this it behaves, and it always remains between 1 and -1. So it means that here comes the inequality, that the sine of any, it can be any, because the domain of sine function is all real numbers, so it can be anything. No matter, here we have x, here we have pi over x, it will always be between -1 and 1, the sine function. So here we have the inequality, and we need two functions here, and a function basically whose limit we are going to evaluate. So the limit of which function we are going to evaluate, because squeeze theorem gives us that, this function. So I'm having sine pi by x, but I'm missing this thing. So I'm going to multiply. So in order to have this full function, I'm going to multiply this inequality with this function. Okay, root x cube plus x square. So multiply this inequality with this. So it will be x cube plus x square negative x cube plus x square sine pi by x. This is 1 multiplied by x cube plus x square is this. Okay, so here we have now the inequality. So it means that this function is lying between these two functions. Okay, so now what we are going to do is, so the next thing is we're going to evaluate the limit at x 0. So here c is 0, and I'm going to check that whether, like, for these two functions, the limit at x equals to 0, when x approaches 0, they are equal or not for these two functions, because that's the second condition. We have the first condition that yes, we have an inequality, these two should also be true. Okay, so we're going to evaluate limit x approaches to 0 negative x cube plus x square, and then limit x approaches to 0 x cube plus x square. And what do we have? 0, 0, negative root 0 is negative 0, 0 is like not negative, not positive, so it's 0. It's 0. Yeah, limits are equal. So these three are true. Then what's the conclusion? That this is our capital F of x. So limit x approaches to c. What was c? It was 0. 0. F of x, what was our f of x? This thing. X cube plus x square sine pi by x. And what should be the answer? P. What is p? 0. So it's 0. Yeah. So here we have the answer. That's it. Okay. So this is how we are going to do this. Now I'm going to give you like the graphical illustration of how this function is gonna look like. Okay. So just wait a moment. I'm gonna do it on my graphing calculator. So this will give you better understanding of the problem and you'll never forget it. Okay. So all the questions on squeeze theorem goes like this. They go like this basically. Okay. So sorry. Okay. Yeah, here we have this. So this is my graphing calculator. Okay. So what was our function? This was our function. Root x cube plus x square sine pi by x. And these two are the functions. Okay. So this function lies between these two functions. This was our inequality. And here, yeah. So from the graph, we see that x minus 1, from x minus 1, it is equals to minus 1 to So from x minus 1 to infinity, to all the x ahead, infinity, this inequality is true. This inequality is true. Yeah, this function is lying between these two functions. So this function is red one, okay, and these two functions are, this is blue one, this is, so this function is lying between these two functions for x belonging to minus 1 to infinity. So this is true. So why, like, the negative x's behind minus 1, they are neglected? Why should this be the case? See this. So if I put minus 2 here, so if I'm going to put minus 2, okay, so this is the case, x cube plus x squared, take this function, I'm going to put x as minus 2, okay, so here put x minus 2, minus 2 cube is minus 8, and minus 2 square is plus 4, so this is negative root negative 4, and this is 4 iota, and this is not defined, this is not a real number, and we're working with x-axis, y-axis, on which real numbers lie, okay. So it means that this is the domain, so this is the domain restriction. If we put minus 1 here, so this is minus 1 cube is minus 1, and this is plus 1 minus 1 square, so we're going to get 0, but if you put less than minus 1, we're going to get negative under the root, that is not defined. So the domain is minus 1 to infinity for these functions, all of these functions, all of these three functions, okay. So this is how their graph looks like, and for all the values of x in their domain, this inequality is true, and this is how this function is sandwiched, it is squeezed between these two functions, and this is the limit. Okay, so we see here too, so we can illustrate the limit using graphical method. So okay, so there was a problem with that. Okay, so here for this function, this blue one, as x approaches to 0, okay, see here this function, this blue one, okay, so it's this one, okay, as x approaches to 0 from the either side, the value of the function goes towards 0. So our limit was, we also calculated 0. Here too, as x approaches 0, the value of the function goes towards 0. And for this function to red one, our main function, as x approaches 0, the values of the function goes towards 0. Okay, so this is how we can solve this question. So now you fully understood this question. What was this question? The graphical illustration, the algebraic manipulation. This is how you solve it. Thank you so much.